Let's now talk about norms, and we have already looked at this, but this is like a video dedicated just for introduction to norms. So norm is simply n- a way we can tell how large a vector is. So let's say this is the vector we have, so how large a vector is, or how long that vector is, or what is the magnitude of that vector. Essentially all the same thing. Basically what we are trying to say is this is the if this is the origin 0, and if the vector is at point, let's say 2 comma 1, then this length of this vector is the norm of that vector. And that's one explanation. There are different types of norm. In this case, let's say if we apply the Pythagoras theorem, what we have is we need to calculate that hypotenuse. So the hypotenuse is equal to the square of this side, which is this is the, if we look around this is, let's say 2. So 2 squared plus, if we go up in the around y-axis, this is 1, so 1 squared, and we take a square root of that, so that's essentially 4 plus 1 is equal to square root of 5. So that's the magnitude we have, or in other words, we can say that that is the norm of w, of the vector w that we have there. Likewise, this is also expressed in terms of squared value. So if it's squared norm, it simply means we just square our square root of 5, and so we get a value of 5. So this is just simpler and makes the math easier. So sometimes a squared norm is used, or sometimes this regular value of norm is used. And the way we read this is we just say norm, this is norm of w, that's how we say, or length of w. And usually it will be a positive value, and as we saw here, there are different basic properties of for these norms, and we'll look at it one by one. The first property for norms is non-negativity. Non-negativity. And what this means is the lengths are never negative. That is to say, if we take the length or the norm of x, then that will always be greater than or equal to 0. The second property is that the norm of a vector, let's say x, is equal to 0 only if it's a 0 vector, only if x is equal to 0. And the third property is scaling or homogeneity. What we mean by that is, let's say we multiply the vector x with a scalar and then take its norm. It's the same thing as uh, uh, getting the norm of x first and then multiplying with the absolute value of the scalar. For example, let's say we'll go with the same example that we have here. We have, let's say, x that is equal to 2 1, that's the vector we have. We take the norm of that, and we know that the norm of x in this case is simply square root of 5, and we assume that a is some value 3. And so what we do is multiply absolute value of a with the value of the norm, and so we get 3 square root of 5 as the answer. Now that's this side. Now for this side, what we do is take the value of 3, multiply it with the value of x that we have. So what we get is 6 by 6 and 3. Then we take the norm of that product, and so the norm of that product is going to be 6 squared plus 3 squared, that is equal to 36 plus 9, and 36 plus 9 is equal to 45. And as we know, we can decompose that to 9 times 5 is 45, and thus we can bring the 9 outside, so that would be 3 square root of 5. And as you can see, this value is same as this value, which is to say that this is same as this, and that's the third property. The fourth property that we have for norm is triangle inequality. Inequality. What we mean by that is, if we take the sum of two vectors and then take the norm of that, it should be less than or equal to the individual sums of these norms. For example, if we have a vector x that is 1, 2, and we have another vector y which is let's say 3, 4. If we try and calculate the sum of these, let's say we calculate x plus y, what we get is 1, 2 plus 3, 4, and that equals 1 plus 3, 2 plus 4. That gets us the value of 4 and 6. Now we try and get the norm of this vector 4, 6 that we have summed, and that's going to be equal to 4 squared plus 6 squared, and that would be, this is 4 times 4 is 16, and 6 times 6 is 36. So we get a value of square root of 6 plus 6 is 12, 1 here, 4 plus 1 is 5, we get a value of 52, square root of 52. Now if we do this the other way around, let's say we get the norm of x first. So norm of x would be square root of 1 square plus 2 square, that is square root of 1 plus 4, that is 5. The second one is square root of norm of y is going to be square root of 3 square plus 4 square, that is 9 plus 16, that is square root of 25. That gets us a value of 5. So if we try to now get the sum of norm of x plus norm of y, what we get is a value of square root 5 plus 5. And if we try to get the actual values in decimals for these, let's see what values we get. So the first one is square root of 52, that equals 7.2, and on this side it was 5, so that's the 5 we have, 5 plus square root of 5, and here we get a value of 7.23. Let's say 236, and earlier what we had was square root of 52, that was again, this was 7.2111. And as you can see, if we look at these decimals after the second decimal, this value is larger, so it does satisfy this condition where this value is smaller as compared to this value that we have. That's the triangle inequality property that the norm must satisfy. Moving on, there is a concept of a standard norm that we just saw, uh, and the standard norm, let's change the pen. Standard norm is, as we said, x is equal to square root of the dot product of x with itself. And so if we have, let's say, a vector that is 3, 4, if we try and get a dot product of it with itself, that is going to be uh, let's say x transpose of x like this, so 3 4 and 3 4, so that gets us 3 times 3, 3 squared, plus 4 times 4 is 4 squared, and that's 25. And this is the uh, dot product, and then for norm we need to put this inside of square brackets. So the norm put inside of the square root, so this is your square root of 25, that is equal to 5. So what this tells us is that this is exactly distance from the origin. So what this is telling us in a way is that if we try and plot a point, so let's say if we try and plot a point, I'm going to draw an arrow here and draw an arrow here, and let's say that is the origin we have. And if we try to look at this, is 1 2 3, so that's 3, and 1 2 3 4, so maybe that's the point we are aiming at. So if that is the that is our uh, vector 3 4, which is x, so this is, we said this was 1, this was 2, this was 3, and this was 1 2 3, and this is 4, that's 0. Then this norm, which is the length of this vector x, essentially is also telling us how far the how far is that point 3 4 from the origin, right? That's what that is telling. It's exactly the distance between the origin and the point 3 4. That was one concept, and then the other concept that I want to talk about is the following. If we look at the formula for norm, which is let's move this up. If we look at mm, x, this is nothing but x1 squared plus x2 squared plus dash 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 xn squared. So we just square each term in the n dimensional space and get the sum. For example, if we had uh, if we had a data point which had like these many dimensions, 1 2 3 4 5 6 dimensions, then the norm of this vector in the 6-dimensional space would be 1 square plus 2 square plus 3 square plus 5 square plus 6 square plus 7 square, and that is also going to be the distance of that data point from the origin. So in simple case, if you look at a 2D vector where we have the value of x as 2 and minus 3, then if we try and take the norm of this, we can say this is 2 squared plus minus 3 squared, and that is equal to square root of 4 plus 9, and so we get a value of square root of 13, that is approximately equal to what? Square root of 13. So let me check. Let's go back. Square root of 13, 3.6055. So 3.606. So this vector has in 2D, this has length of about 3.6. Likewise, if we look at another vector, x is equal to 1 to 2, then we would take the norm as such, a square root of 1 square plus 2 square plus 3 again 2 square, and so that is going to square root of 1 plus 4 plus 4, that is equal to 4 plus 4 is 8 plus 1 is 9, we get a value of 3, and so the length of this vector in 3D is 3. And there's another important concept that we need to look at, and that is normalizing with vectors. So why do we normalize? And so we are going to talk about normalize, and the reason we normalize vectors, and that's important neural nets, is to make all inputs to make all inputs have the same length. And so we don't have features, some features dominate with larger values dominate, and that's one of the reasons you may heard that we always normalize the data if we have values in certain column that are way larger in magnitude than others, say a million as opposed to values in between 1 and 10 in another column. So if we look at an input p, then what we are aiming to do is the norm should be 1. So that's what sort of the target is. And to and so uh, uh, to normalize a vector, what we do is divide it by norm the length of p. Let's say we have a vector 3 4. So if you are trying to normalize a vector 3 4, so here I'm going to just write this as p is equal to 3 comma 4, and here if we calculate the norm of p, that is going to be 3 squared plus 4 squared, that is equal to 9 plus 16, that is equal to square root of 25 is equal to 5. That's the norm. Now we need to normalize it, so we are going to do this. We take the value of p and then divide it by the length of that vector, and so what we do is divide this vector by 5, which is 3 4, and so after normalizing we get value of 3 divided by 5 is 0 0.6, 4 divided by 5 is 0 0.8. And so this is now a normalized vector, and what we are saying is that it would have a length of 1. Does it really have a length of 1? We can check that by calculating its length or norm, and to do that we simply take the square root of each of these, add them up, and take the square root of that. So this is going to be 0.6 into 0.6, so that's 0.36. This is 0.64, and if we now add those two, so if we add 0.36 plus 0.64, we get square root of 1, and that is equal to 1. And so that does satisfy this condition that we said, that after we normalize, the length of that vector becomes 1. And this is again very common in neural nets, because when we compute these dot products with W transpose P, we often want them to represent pure similarity and not have any one feature dominate this particular scalar value that we get from this. Finally, the norm, we also use it in calculating the angle between two vectors, and we have seen that this in one of the previous videos. So what we say, if we are trying to calculate angle between vectors, we would simply find cos theta is equal to the dot product of x and y divided by the norm of x times the norm of y. And so if we have, let's say, a vector x that is equal to 1 2, have another vector y which is say 2 3, and we can try and see how they look. So that's let's say that is our coordinate axis. This is 1, this is 2, and then this is 1, this is 2, and this is 3. So our 1 2 vector would be somewhere here like so, and our 2 3 vector would be, this is 2 and this is so, oh, it would be somewhere right there. So let's use a different color, so probably somewhere like this, and we are trying to find maybe the angle between these two. Not exact drawing there, but I hope you get the idea. To get the angle, we calculate the dot product between these two, so that's going to be the uh, transpose of x times dotted with y. So we have 1 2 dotted with 2 3, that gets us 1 times 2 is 2 plus 2 times 3 is 6. We get a value of 8. So that's the dot product we have, also written as x comma y inside of parentheses. So we now have the numerator. All we need is the denominator. So norm of x is equal to square root of 1 square plus 2 square. We get 1 plus 4, that is equal to square root of 5. Likewise, we get the norm of y, that is equal to square root of 2 squared plus 3 squared. So that is equal to 4 plus 9, that gets us value of 13. And the square root of 5, that is approximately equal to 2.236. This is approximately equal to 3.606. And so if we plug that in to get the value of cos theta, that would be 8 divided by 2.236 multiplied by 3.606, and let's see what we get there. So that's 8 divided by 2.236 divided by 3.606. We get a value of 0.99, and then if we round it up, we get 3. So now if we take the uh, cos inverse of this, cos inverse of 0.993, we get value which is theta is equal to cos inverse of 0.993, gets us value of 6.78, or about 7 degrees. And that makes sense. It's pretty small angle that's there between these two, and looks like 7 degrees. So that what that tells us is both these vectors x and w, x and y, are pointing in the same direction. They're pointing in the same direction because the angle is so small between them. And so that's how these norms help us in neural networks. And so to summarize all of this again, the first thing is that the norm, we calculate it by simply taking the square root of dot product. Then we can say that it's a square root of dot product, and that gets us the length or magnitude and or dot product, or we could say this is simply x transpose x. So it means the same thing. Then we can use it for normalization so that vectors have a length of 1, and so if this x cap is normalized vector, we get that by dividing the original vector by the norm or length of that vector, so that it has a length that equals 1. And then we can also use norm to calculate the angle, and the cosine of angle between any two vectors would be the dot product between them, and then the norm or divided by the norm of each of those, and that helps us find the cosine, that helps us find the similarity on the direction of those two vectors. And in neural nets, as we know, we calculate the value of w transpose p plus b, and here the inner product that we do, which is this one, of the inputs and weight, this measures how aligned the input is with the neuron's pattern, which is w, is p with uh, w. And so it's important that none of the inputs with large magnitude dominate, and so normalizing the inputs uh, could help in this case when we are training neural networks. So that was it for this video. I understand there are different types of norms, generalized versions of norms. We won't go into the details right now, but there is a general definition I'll leave you with. So if we have x of p, we can say that the norm of x1 raised to power p plus x2 raised to power p, and then the square root of p. So we can replace p by any number from 1 to infinity, and that is going to be the norm. For example, in case of the squared norm, when we say a squared norm, we essentially raise this to the power 1 by 2. That is to say, we get the square root, and square root of what? We take each of these and then square these as we saw earlier. So if you are looking at norm of maybe 3, then this would be uh, x1 raised to power 3 plus x2 raised to power 3 and so on, and then this would be 1 by 3 right here. So depending on the use of norms, uh, uh, different types of norms are available that can be used. And so essentially what we are trying to say here is that there are so different norms are different norms are just different ways to normalize the vectors. So because the normalized length that we get, which is this one, would be different if we normalize x in a different way. That's just a general idea there. I hope this was helpful. Looking forward to seeing you in the next video. Please like, share, and subscribe. Thank you.